In this video, we are covering the dot product. So at this point, we know how to add and subtract vectors, right? We can take vector A and we can add vector B, and we'll get the resulting vector by just adding the corresponding components of these two vectors. And we can also subtract two vectors, so we'll just subtract the corresponding components to get the new vector. And we also know how to multiply a vector by a scalar. So for example, consider the vector 2 and 5. And if I were to multiply this by -3, which is a scalar is just, think of it as a constant number, right? It's a number that we are going to multiply by these components in this case. So we'll take -3 times 2 and we'll get -6. And then we'll take -3 times 5 and we'll get -15. Okay, that's scalar multiplication. So we made the point in the video on vectors that was scalar multiplication. What about multiplying vectors? What is vector multiplication? So, as if things couldn't get any worse, there are actually two types of vector multiplication. So the first one is the dot product, and the second one is the cross product. And you're probably thinking, how did we get to these names, dot product and cross product? And you'll see how ingenious the naming is once you actually look at the operations. So the first one, which is what we're covering in this video, is the dot product. So the dot product is the first type of vector multiplication. Now the dot product of two vectors, and here we have vector A and its components are A1 and A2. And then we have vector B and its components are B1 and B2. So here's what the dot product is. It's vector A dot, hence the name dot product. Again, the naming is ingenious. So we have vector A dot product vector B, and how we obtain the result is we take the first component of A and multiply it by the first component of B, so A1 times B1. Then we're going to add to this the second component of A multiplied by the second component of B. Now this is for a two-dimensional vectors. What about the dot product for three-dimensional vectors? And here we have it. So it's A dot product B. It's going to be A1 times B1, A2 times B2, and then the third components, you'll multiply them and then you add them. So note that the dot product of two vectors, it's yielding a scalar number. Scalar number, what I mean by that, a constant number. It's just yielding a number. It's not yielding another vector. So this is a number. It's not a vector. This is a number. It's like 5, 6, 7, whatever the case is, -200, -1 billion. Okay, it's giving us a number. Now, this scalar number, or the dot product, is obtained by multiplying the corresponding components of the two vectors and then adding the products. Now, this may seem like a handful. All you have to do is take component 1, multiply it by the component 1 of the other vector, and you'll get an answer. And then do the same for A2 and B2, multiply those together. And then if you have a three-dimensional vector, you'll have three components. So you'll take A3 multiplied by B3, and you'll get an answer for A1 and B1, A2 and B2, and A3 multiplied by B3, and then you just add them all up. Okay, so you're multiplying the corresponding components, and then you're adding them up. It's that simple how to calculate a dot product. All right, exercise 1, time to see if you learned what a dot product is. So find A dot product B and B dot product A given the following vectors. All right, let's do this example. This isn't rocket science. So A dot product B. So it's equal to, you take the first component of A, which is 3, and you multiply it by the first component of B, which is -4, and then you add the second component of A, which is -6, multiplied by the second component of B, that's 5. Okay, there we go. So it's 3 times -4, that's -12, plus -6 times 5, which is -30, and your answer is -42. It's that simple. Okay, there's nothing complicated about calculating that dot product. And let's think about what happens when we take B, vector B dot product A. What do you think is going to happen, or what would the answer be without doing the calculation? Well, it's the same thing. It's going to be the exact same answer, minus 42, because what we're going to do is take minus 4 times 3, that's going to give us minus 12, and then 5 times minus 6, that's going to give us minus 30, and then we're going to add those up and get minus 42, and there's your answer. Okay, so the order in which we perform the dot product does not matter. All right, and that's example 1. Okay, exercise 2. So you have now two vectors, but these vectors are now three-dimensional. So I want you to find A dot product B and B dot product A. Okay, let's go for the answer. So A dot product B, we have established, and this is one of the properties of the dot product, that it's the same thing as B dot product A. It doesn't matter in what order we multiply. Okay, as long as we are multiplying them and we do that multiplication correctly, we'll get the correct answer. Okay, so it's going to be 35 times 2, that is going to be 70, plus we have 7 times minus 3, that is going to be minus 21. I multiplied the second components, and then plus we have minus 9 times by 2, that's minus 18. So it's going to be 70 minus 21 minus 18. If you work that out, it's going to be positive 31. Just be careful with your signs. Okay, so it's 7 times minus 3, that's minus 21, minus 9 times 2, that's minus 18. Okay, and the dot product here will give you 31. Now, if you're asking, okay, I know how to calculate a dot product, why am I learning this? What is the significance of this dot product? Don't worry, we're going to cover that in a few slides. There is a reason for this dot product, and it's pretty cool. So the dot product has the following properties. So if I have some general vector A, and this vector can be either two-dimensional, so it can have an X and Y component, or it can be three-dimensional, so it can have an X, Y, and Z component, right? So two-dimensional, three-dimensional, these properties are still going to hold. Let's go through it. Let's just work in 2 dimensions because it's simpler to explain. Okay, it also extends to 3 dimensions. Okay, A dot product. So we have some general vector A, and it has a general components X and Y. It can be any real number that you want. So A dot product with itself, it is equal to the magnitude of A squared. Now let's think about why. Let's just go through this first property. That's probably the most complicated one from this list. So if I have A dot product with itself, I'm basically going to have another A vector, but it's the same thing. I'm just copying this down. It's the same vector. So it's X and Y. So it's going to be X times X, that is X squared, plus Y times Y. No surprise, it's Y squared. And then what is the magnitude of A? So if we recall from the lesson on vectors, the magnitude of A is defined to be the square root of, and then we have to square each of these components. So we take X squared and add to it the square of each of the components. So it's Y squared, so it's two-dimensional in this case, right? And then if I square this, so take a look at this, we have the magnitude squared. Now, if I square this on the left-hand side, I have to square this on the right-hand side, which means I basically get rid of the square root sign. So the magnitude squared is equal to X squared plus Y squared, and the dot product of A with itself, so A dot product A, is going to be X squared plus Y squared. Okay, so that's probably the trickiest property here. The rest are absolutely easy. Okay, let's go for the second property. So this time I'll consider a different vector because all of these are dealing with two different vectors. So instead of X and Y, let's call this A1, A2, and now we'll have vector B that's equal to B1, B1, and B2. So A dot product B is equal to B dot product A. So the order in which you perform the dot product doesn't matter. Okay, we've seen that in the previous two examples. Then A dot product B plus C is equal to A dot product B plus A dot product C. So let's just take a minute and think about why this is the case. Let's consider another vector C, and that will be C1 and C2. So we have A, and instead of dot product all the time, I'm just going to say dot. It's easier for me to say. And now what we have here is B plus C. So let's get that vector, right? So it's going to be this component plus that component. It will be B1 plus C1, and the second component will be B2 plus C2. So B2 plus C2. So that's the resulting vector B plus C. Easy, right? And then what we're going to do is A, we need to have A1 and A2. I'm just writing out the components of A. A1, so it's vector A dot, okay, dot B plus C. And now we just need to perform this dot product operation. So we'll take A1 and multiply it by B1 plus C1. So it will be A1, B1 plus A1, C1. That's the first component. That's the first component being multiplied by the first component of this vector here. And then we'll take the second component, A2, and multiply it by the second component of that vector. So it will be plus A2B2 plus A2C2. Okay, and then we can do some rearrangement. So what I'm going to do is I'm going to take this A2B2 and write it next to the A1B1, and you'll see why I'm doing that. So it's A1B1 plus A2B2, and then it's going to be plus A1C1, okay, plus A2C2. So I haven't done anything, I've just rearranged the order. Now what's A1B1 plus A2B2? Well, that is the dot product if I take vector A dot vector B. So I want you to try that. Take vector A and dot product, have it dot product with vector B, and you'll see that you'll get A1 B1 plus A2 B2. And then what's A1 C1 plus A2 C2? That's vector A dot vector C. Okay, so that's how the third property works. All right, let's go for the fourth property. So the fourth property states that if you have a constant or scalar number multiplied by A, and then it's a dot product with vector B, that's equal to the constant multiplied by the dot product of the two vectors. Or you can have A, okay, A and then dot product, that constant or that scalar times the vector B. This one is basically saying, hey, it doesn't matter where you multiply that constant, at the end, you still have to multiply that constant. So you can multiply it by vector A, you can multiply it by the actual dot product, or you can multiply it by vector B first. It doesn't matter. Just do the multiplication wherever you want to. Okay, so that's 4, and you can prove that one. So just pick a constant and work with these two vectors here. You'll see that if you work what this is and what that is and what that one is, it's going to be the same thing. Now, the fifth one, we have the 0 vector dot vector A, and that's going to give you 0. Note, okay, that it's not going to give you another vector. It may be a bit confusing at first, or you may be tricked into thinking that, hey, it's the 0 vector, shouldn't give us a 0 vector. No, the dot product gives us a scalar number. Let's think about it. Let's do an example. So let's get this out of the way. We have A1, all right, A2 with 0 and 0. That's the 0 vector. Remember, the 0 vector has all zeros as its components. Again, it would be kind of weird if I said a 0 vector has like a 7 as its first component. That would be crazy. Okay, so there's the 0 vector, and you just have to perform the dot product. So A1 multiplied by 0, well, that's 0. Okay, 0, and then A2 multiplied by 0, that's going to be plus 0. And then we add these up and we'll get 0. So it's a 0. It's the constant number 0. It's not going to be another vector. So those are the basic properties of the dot product.